All right. Here we go. So, what we are going to be looking at for the next few weeks has to do with explaining a lot of stuff that we've sort of already talked about. We've already talked about ionic compounds, okay, and how they involve the transfer of electrons. We're going to spend most of our time talking about covalent compounds with the sharing of electrons and how that works, okay? But we need to sort of wrap up a few little details about ionic compounds. And all this stuff is stuff we're going to do in the context of sort of talking about dyes and food coloring and stuff like that. We're going to do some labs and other activities around that kind of stuff. So, it turns out that ionic compounds, while important to dyes, don't make very good colored compounds. The color is, you can't get a very good range of colors. And so ionic dyes are probably not the way to go if you're looking to make a textile business. So, to understand why that is, and then to move on to understanding why organic or covalent compounds would probably be a better idea, we need to understand a little bit more about what are ionic compounds. Okay? So, most ionic compounds in the solid form come as regular repeating crystal structures. So, in an ionic compound, such as this one here, what you typically see is this regular repeating lattice work of positive and negative ions. We have had a transfer of electrons, in this case from the chloride ions to the sodium, right? Chlorine gained an electron. This chlorine gained an electron from the sodium, say, and became sodium chloride, a transfer of electrons. The sodium lost an electron, forming a positive charge. The chlorine gained an electron, forming a negative charge. We always have this repeating pattern, okay, where these bonds here, these sticks, represent the attractive forces of the positive ions for the negative ions. Because positive and negative attract, while negative, negative, and positive, negative, or positive, positive repel, you always have this repeating pattern where you alternate positive, negative, positive, negative. There are actually a ton of different crystal types, different ways that the atoms can pack and arrange together, none of which are important for the test that we're going to take. So we're not going to worry too much about them. But know that there are different types of internal structures, that you get different shaped crystals and all kinds of fun stuff like that. It's a really fascinating branch of chemistry that is beyond the scope of this class. So, these regular repeating crystals are generally highly organized. They generally give us macromolecules, molecules that are very large. A salt crystal is generally one whole molecule. That's why they typically have very high melting points, for instance. Ionic compounds, typically very difficult to melt. You have to heat them up to hundreds or thousands of degrees because they are held together with these strong ionic bonds. Okay? Now, what we want to talk about briefly is how can we compare the strength of one ionic bond to the strength of a different ionic bond. Okay, we want to talk about what we call the lattice energy. And so the lattice energy is, if we look at this crystal, it's the strength of the attractive force between the positives and the negatives. And so because it's what we call a Coulombic force, it's based on Coulomb's attraction, electrostatic attraction, the attraction of a positive charge for a negative charge. The lattice energy is proportional to the charge on the ions, +1, -1 in the case of this sodium chloride crystal, divided by the distance between them, squared. So where R is the distance between the two nuclei, the internuclear distance. Okay? So, the bigger the charge, the larger the lattice energy. Okay? The bigger the charge, the larger the lattice energy. And the smaller the radius, the larger the lattice energy. So what we want to do when we are asked to do this, and what we're asked to do is just compare. You'll be asked to compare sodium chloride to magnesium chloride. And what you're asked to do is to think about, well, how do the charges compare? And how do the distance or the radius compare? And we can get radius. We're just going to estimate these things. We're not really going to have to do calculations with this. Okay? We need to be able to make estimates based on what we know about the periodic table and the trend in the sizes. Right? As we go from left to right across the periodic table, size will decrease because of more protons in the nucleus. As I go down the periodic table, then I would expect the size to increase because the electrons are at higher energy levels further away from the nucleus. So larger ions have a lower lattice energy. And generally, if you go over on the periodic table a couple of elements, that's equivalent to changing the charge by 1. All right? So what you have to do is you have to think about questions like which one of these pairs of ions would have the larger lattice energy? Magnesium chloride or sodium chloride? What do you have to think about? What are the two things you got to worry about? Size and charge. So write down the charges of all the pieces. Okay, then look at a periodic table and say, how do the sizes of these things compare? Okay, take a minute right now and do that. Write down the charges of all the things, look at the sizes. So did you get magnesium has a +2 charge, right? Second column on the periodic table. The chlorine is a -1, second to last column. How does the magnesium charge compare to the sodium charge? Sodium is a +1, but chlorine is a -1. Now, what about size? Which one's going to be larger? Sodium or magnesium? Sodium will be larger, chlorines will be the same. Why is sodium larger? Less protons in the nucleus. They both have the exact same electron configuration. They both have the same electron configuration because magnesium's lost 2, sodium's lost 1. They both have electron configurations like neon. So magnesium has more protons, therefore it has a smaller radius. So the magnesium has both a smaller radius and more charge. So that means that our magnesium chloride is going to have a higher lattice energy than sodium chloride. You will most likely not be faced with situations where you have to judge between size and charge. You'd have to really do the math to make that work out, so it's not something you're going to have to deal with. Nope. The number of any one of the ions doesn't matter. We just look at the charge on one of the ions versus the charge on one of the magnesiums. Now, lattice energy itself, what it really is it's a measure of the strength of the ionic bond. Technically, what lattice energy is the amount of energy released when two gaseous ions, that is ions in the gas phase, condense to form a solid, okay, to form an ionic crystal. So lattice energy is the amount of energy released when two gaseous ions condense to form a solid. Question? Well, again, we're not going to do the math with this. So we're just going to know that that means the size. And so the larger the ions are, the lower the lattice energy will become. And so there's a K here. This is some proportionality constant. But again, don't worry. I'm not asking you to, we're not going to do math with these. It's just going to be compare one thing to another thing. Okay? All right, so here we are. We have lattice energy calculations. We can do make some judgments between one pair of ions and another pair of ions. But we still haven't sort of really answered the question. What makes some bonds, the ones between metals and nonmetals, as we've talked about, ionic versus other bonds being covalent? Why do we have these two different sets of bonds? And to do that, we need to talk about another property from the periodic table, the fourth one from that video, the one we didn't really watch. We need to talk about what we call electronegativity. Okay? And electronegativity has a trend in the periodic table. This may look very similar to other trends that we've seen. This is a sort of graphic representation of the strength of the electronegativity. And what electronegativity is a measure of the attractive force that an atom has for shared electrons. So if I bring two atoms together and their orbitals start to overlap, they will both be able to attract the electrons in those orbitals that are overlapping. And so what we want to do is we want to say, well, if one atom attracts those electrons very strongly and the other atom does not, then it's possible for the electron to be transferred from one atom to another, and that would form an ionic compound. But what if one atom sort of attracts and one sort of attracts but not as strongly? Okay? In that case, what we have going on is they are going to share the electrons, and we'll form what we call a covalent bond. Now, it turns out that this idea, that's right, what we've been talking about, this covalent versus ionic, it's not a binary situation. It's not ionic or covalent. There's actually sort of a spectrum, a gray area. And what we want to do is we actually want to sort of look at how strongly different atoms attract electrons and make a judgment whether the thing is going to be ionic or covalent. To do that, we need to look at these electronegativities. Now, we can look at them here. We know the trend. As I go across a period, the atom's going to attract the electrons more strongly. Okay? Fluorine has the highest electronegativity. Oxygen is next, and then nitrogen. Then chlorine comes after nitrogen in terms of the value for the electronegativity, the strength of the attraction. And so we can look at this sort of graphically, but we can also, there are numbers, these are values that have been measured. So if we go ahead and take our periodic table and flip it around to the crazy backside of the periodic table, it looks the same, but different, okay? So this periodic table has a whole lot more information. And again, the key is, of course, the place to go to figure this out. We have the symbol. There's a little representation of the crystal structure here, which is kind of cool. They talk about the radius, the covalent and atomic radius. They talk about the atomic volume. They give us the ionization energy, the first ionization potential, specific heat capacity, thermal conductivity, electrical conductivity, heat of fusion and heat of vaporization. We'll talk more about those later. And finally, electronegativity. So if we look on this periodic table, for instance, on oxygen, the electronegativity is 3.44. And then we could look at the electronegativity of hydrogen, 2.20. Now, the difference between those two values tells us how much ionic character the bond will exhibit. And we'll get to what that means in a little bit. But for a covalent bond, remember we said, that it's not ionic or covalent, that there's this spectrum. You can be totally covalent. You can be someplace in the middle. Typically, we call that polar covalent. And you can flip over into being ionic, okay, with a separation of charges. So we look at these values and we look up the difference in electronegativity, and that will give us the percent ionic character. Okay? Typically, once you start to get to about 1.5, 1.7, someplace in here, about 50% ionic character, you typically start to be considered ionic. So you can see that, for instance, water, which we know to be covalent, 2.2 versus 3.44, that's a difference of 1.4, is 39% ionic character. That's a lot of difference in electronegativity for a covalent compound, one of the highest. Okay? But because if you tip over a little bit further, for instance, if you look at something like oxygen with lithium, lithium has a value of about 1, then we have a difference of 2.4, 76% ionic character. Well, lithium oxide is a completely ionic compound. Okay? So, it's not yes, no. There's a scale. And the further apart your atoms are on the periodic table, the greater their difference in electronegativity will be, and the more ionic the bond will be. Okay? So typically, with the exception of hydrogen, if you are a nonmetal combining with a metal, the difference is great enough that you are an ionic compound. Okay? But hydrogen is sort of the exception. Notice it has a pretty large or exceptionally large electronegativity for something in the first column. Right? Electronegativity decreases as we go down. So something like cesium or francium have the lowest values on the periodic table, whereas fluorine has the highest. All right? So greater difference, greater spread on the periodic table, bigger ionic character. And that's going to have a lot to do with what we call polar covalent bonds, we're going to talk about in a couple of days. So, we can look up values on here, but for the most part, we're just going to need to make some judgment calls. So, if we wanted to say, look at this, if I gave you a pair of bonds and I said, which pair would have more or greater ionic character, HCl, H with chlorine, or H with fluorine. Fluorine has a bigger electronegativity than chlorine, so we would expect HF to have a greater difference in electronegativity than HCl, and it does. HF has a difference of, 1.8 versus HCl has a difference of about 1. Okay? So, generally for the ionic bond stuff, we don't really have to do any calculations. In fact, for most of this unit, it's not a math-heavy unit. It's more of the theory stuff. Okay? Our next unit, chapters 3 and 4, which we'll go to in like 2 or 3 weeks, that's where we really start to get into the math of chemistry. Okay? So this is, we do another sort of theory unit. This one's a little bit more visual. It's a little bit easier to visualize. There'll be some modeling activities we can do and stuff like that. But not a lot of math here, more theory. So you got to sort of think about these things, realize that the bigger the difference on the periodic table, the greater the difference in electronegativity, the more ionic character the thing is going to have. All right? Now, ionic compounds are great for all kinds of things, but in the case of the dyes that we're trying to make, they're not going to give us the kind of colors we want. To get those kind of colors, we really need to figure out covalent compounds. We need to look at polarity of the molecules, how they bond onto the dyes, and the sort of way that electrons are arranged inside molecules that are going to help us figure out why they produce the different cool colors they produce. Okay? To do that, we're going to need what we call Lewis structures. And Lewis structures are sort of our introduction to understanding how atoms bond covalently. And that's what you're going to learn tomorrow. Okay? Excellent.